Hi everyone, welcome to a quick video on acid-base equilibrium problems. So we may have seen a little bit of this kind of thing in Gen Chem, but I want to approach it from the organic chemistry perspective. Sometimes you may be asked to evaluate an acid-base reaction and will want to know which side of the equilibrium is favored. So to go about this type of question, there's 3 steps that I like to follow. First thing, we need to determine which is our acid and which is our base. In the generic example above, I give you A for acid plus B for base, but that won't always be the case. Sometimes you may look at it and be like, yeah, obviously that's the acid and that's the base. Other times it may not be so clear. So if I were to give you HCl, for example, you might already know, even just from general knowledge, that that's hydrochloric acid. When it comes to more organic-based acids, you could be given something like this. This is acetic acid. Again, the key's in the name there. But if you don't know the name, you might not be sure if this is an acid or a base. And if we are saying, yeah, it's acetic acid, it's probably an acid, there's still other questions that you have to confront. We have a proton that's drawn out for us right there. That could be the acidic proton, but there are other CH protons here that we can't rule out, so we'll have to analyze those separately. Yet another example could look something like this, where we don't have any protons drawn in whatsoever. And so we'll have to analyze very carefully, are there acidic protons or is it more likely to act as a base? Second, the conjugate acid and conjugate base, or Ca and Cb, won't necessarily be provided for you. So that means that you're going to have to draw them in. When doing this, you want to be careful to replicate these starting materials exactly as they were given to you while just showing the change in position of one proton. It can be really easy to forget to double check your carbon count or draw in things like the double bonds in a benzene ring. So make sure you check those details before moving on to another question. Last but not least, with our acid and base and our conjugate acid and conjugate base, we can then start to compare them to decide which side of our equilibrium is favored. So you want to compare your acid to your conjugate acid or your base to your conjugate base. Pick whichever one makes the most sense to you and stick with it. Either way, we always want to favor the side that has the weakest acid or base. Let's try this out in a couple example problems. First, to get us warmed up, an example that may feel a little bit easy or obvious to some of you, but it never hurts to go through just for practice. So if we were given HCl plus NaOH is in equilibrium with question mark, and we're asked to draw the products and predict the equilibrium direction, let's start with step 1 by deciding about and labeling our acid and our base. Again, your common knowledge may come in handy here, but if you weren't sure, you want to look for which species have protons they can donate and which species have lone pairs or negative charges that can accept those protons. So our HCl is the acid, and our NaOH, with its lone pair electrons and negative charge, is going to be our base. Now, let's draw in our conjugate acid and conjugate base. HCl gives away its proton to the OH minus of NaOH to make water, and what's left over is the chloride anion from HCl and the sodium cation from NaOH. Now let's label those as conjugate acid and conjugate base. The conjugate acid is always going to come from the base, and the conjugate base is always going to come from the acid. That can be a little tough to remember, so try to keep in the back of your mind that when you do the acid-base reaction, it flips. The other way to think about it for this example is that Cl- can't be the conjugate acid because it no longer has a proton to give up, so that must be our conjugate base. And the water, by extension, must be our conjugate acid. The sodium here is just a spectator ion. Now, we want to compare the strength of our two acids to decide which side of this equilibrium is favored. Your common sense may tell you which is the stronger acid and therefore which side is favored already, but if you're not sure, you can always go back to pKa values. The pKa for HCl is -8, and the pKa for water is about 16. In order for an acid to be weaker, we want to have a high pKa value. So water having the highest of the two pKa values must be the weakest acid. So that tells us that the forward side of this reaction is favored. You may already know this from Gen Chem, where we learned that if you combine a strong acid and a strong base, you're going to get an acid-base neutralization reaction where you make water and a salt. Let's move on to a slightly tougher example. In this example, we're given butyllithium and some other organic-based molecule. So, which one is our acid and which one is our base? This one is a little tougher to tell, isn't it? First things first, what's butyllithium? You may or may not have come across this as a reagent yet, but hopefully you can use your knowledge of nomenclature to help you figure out the structure. If we have a butane chain, that will look something like this. And then the lithium part sometimes is drawn like this, as a covalent bond to that carbon. This is not my preferred way to draw butyllithium because lithium is a metal. It doesn't really like to be covalently bonded. So instead, I like to draw butyllithium as a carbon that bears a negative charge as an ion pair with a lithium that wants to give up its electrons to become a positively charged ion. So is that an acid or a base? It does have protons, but it also has a lone pair of electrons represented by that negative charge. So off the top, you may not be certain whether this is going to act as an acid or a base. Let's look at the other component and come back to it. The other component here is a carbon and hydrogen-based organic molecule. Again, this doesn't really look very distinctly like an acid or a base, but this one doesn't seem to have any free lone pairs of electrons, so we should assume that this is going to be our acid. By extension, that means that the butyllithium must be our base. So we're ready to just move on to 2 and start drawing our conjugate acid and base, right? Well, I think there's a little more we need to consider here. If you look at the structure of A, there aren't any drawn in H atoms that are really obviously the acidic proton there. So I'm going to add a little step 1.5 to our list here to remind ourselves that if we have multiple protons or multiple lone pairs of electrons, that we need to decide which one is the most acidic proton or the most basic pair of electrons. When looking at our acid, we have a number of different types of protons here, so I'm going to label them in different colors, and then we can decide between them. To start with, in orange, we have a hydrogen attached to an sp3 hybridized carbon. Next, we have 2 different hydrogens here in green that are both attached to sp2 hybridized carbons. In purple, we have another hydrogen attached to an sp3 carbon, and last but not least, we have a hydrogen attached to an sp hybridized carbon in red. They're all fairly similar except for their hybridization, and that's going to be the deciding factor of which one is the most acidic. Between these options, the most acidic proton is going to be attached to the carbon that has the most S character in its hybridization, or the proton attached to the sp hybridized carbon. Higher S character corresponds to higher orbital electronegativity, but we'll talk more about that in a moment. With our most acidic proton decided on, now we can finally go about drawing our conjugate acid and conjugate base. We can see the butane chain, which was our base, has picked up that red hydrogen and now become our conjugate acid. By extension, then the alkyne anion is our new conjugate base. Last but not least, we want to compare acid strength to decide which side is favored. Although I'm going to change this out and instead compare base strength this time. You use whichever one makes the most sense to you. If we compare our base, butyllithium, to our conjugate base, the alkyne anion, they're going to be fairly similar. So how do we decide between them? We want to think about which one is best able to stabilize that negative charge. Carbon doesn't really like to have a negative charge, so we want to be able to stabilize that as much as possible. And this is where we come back to orbital electronegativities. The negative charge on butyllithium is housed in an sp3 hybridized orbital, whereas on the alkyne anion, it's held in an sp hybridized orbital. The higher S character of sp orbitals is more electronegative than sp3 orbitals, so the alkyne anion is more stable than butyllithium, making it a weaker base. Because of that, we predict this reaction should proceed in the forward direction. Again, if you don't prefer to compare bases, you can always pull up the pKa values and compare the acids instead. Now that we've had some practice identifying acids and bases and predicting which direction of an equilibrium is favored, we can delve into these problems to think with a little bit more detail about not only which side is favored, but how much it is favored over the other. In order to do that, I want to introduce one further tool called delta pKa. What is delta pKa? It's just like taking the delta of anything else. If we take the pKa of a product and subtract away the pKa of our reactant, then we can tell the difference between those two acids, and that's our delta pKa. Now, the delta pKa can tell us 2 important things. Firstly, the sign of delta pKa will tell you which direction of the reaction is favored. A positive delta pKa tells you that the pKa of the product was higher than the pKa of the reactant, meaning that the product is a weaker acid and the forward direction of the reaction is favored. If we have a negative delta pKa, That means that the pKa of our reactant was higher than our product, which tells us we actually would have made a stronger acid product than what we started with. That tells us that the backwards direction of the reaction is favored. Secondly, the magnitude of our delta pKa can tell us the extent to which one side of the reaction is favored over the other. Now, these delta pKa values exist on a continuum, and therefore you can't necessarily say it's cut and dried that exactly at this point it switches over. But these are some benchmark values to give an idea of whether or not the reaction is equilibrating back and forth fairly evenly or unevenly, or if it's just totally favoring one side over the other exclusively. So if the magnitude of your delta pK is somewhere between 0 to 6, that means that there's not really that big of a difference between the strength of the two acids you're comparing. Because of that, the two species are going to be equilibrating back and forth with one another with relatively even populations on either side of your arrow. If your delta pKa is between 7 and 11, this is a little bit of a gray area. You're probably still equilibrating to some degree, but one side of the reaction is going to be strongly favored over the other. If your delta pKa is greater than 11, that means that there is a really, really big difference in the strength of your acids or bases in the reaction, and that it's going to go all the way to one side or the other. With this practice of determining and analyzing acids and bases, I'm confident you can tackle any acid-base equilibrium questions. And with this added tool of delta pKa, you can take your knowledge of acid-base reactions and equilibrium forward into other parts of organic chemistry, say like mechanism drawing, where you might need to decide, where do I do a proton transfer? What would be the acid and what would be the base? Delta pKa can tell you what's a feasible reaction, what's not a feasible reaction, and which ones are in equilibrium or would exclusively go to one side or the other. If you have any questions on acid-base equilibrium or delta pKa, leave it in the comments. Thanks for watching.